Hello and welcome to the lecture Generative AI for Vision Task Part 2. In this lecture, we continue to understand different generative AI approaches for downstream vision tasks like image-to-image translation, medical image synthesis, anomaly detection, 3D scene generation, face synthesis, trials transfer, and video generation. Our next vision task is image-to-image translation. Now, image-to-image translation is a computer vision task which transforms an input image from one visual domain to another visual domain. That means, let there is a grayscale image and we want to transform this grayscale image to a color image by learning a model. This is called image-to-image translation. While transforming, it preserves its underlying semantic content and structural information. That means even when we are transforming to a color image from a grayscale image, the image content and structural information remain same. So this is very important task. There is a lot of application in different other computer vision applications. The objective is to learn the mapping between source and target instruments. So you can understand there is basically two domains. One is source domain, other is target domain. And generally, we try to learn the mapping between source domain to target. This mapping function or this mapping model enables applications such as styles transfer, image colorization, image enhancement, semantic level to image synthesis, day to night translation, sketch to photo generation, medical image model conversion, and so many more. So you can see that this kind of image to image translation is a lot of computer vision applications. The traditional approach basically which rely on the handcrafted feature processing or feature extraction. The modern methods employs a deep learning also, particularly generative AI based models, realistic and high quality. That we'll see in our later discussion. Now, what are the main generative models that are being used? Basically the same as before, GAN, cycle GAN, pix-to-pix, diffusion models, transformer-based architectures, which basically learns the complex cause-domain relationship and generate visually consistent images, while improves texture, color fidelity, and semantic accuracy. That is used for this kind of application. Now here you can say that summer and winter image-to-image translation. So image-to-image translation has become an essential technology in autonomous driving, medical imaging, remote sensing, digital content creation, augmented reality, computer graphics, etc. Where accurate and realistic visual transformation is required. Here you can see that the content-wise both images are very much similar, but the domain means it is a summertime, it makes the winter. And here the reverse, winter is given summer. So that is the domain kind of transformation, where the accurate and realistic visual transformation is critical and downstream analysis and decision making because of this. Now, how generative AI helps in this image to image translation? Now, generative AI for image to image, shortly said I2I, is a deep learning technique that transforms an input image into a new image while preserving its underlying structure and semantic content. Unlike text to image generation, I2I models use an existing image as a conditioning input and modify attributes such as style, color, texture, resolution, objective, etc. These are the different image attributes that is used as a condition. Modern approaches that employs this conditional GAN, variation of encoder, diffusion model, transformer-based network to learn the complex mapping between source and image domains. And during the training, this model optimizes the reconstruction, adversarial, and perceptual losses. So these losses are very important to generate the realistic, high-quality outputs that maintain the spatial context. So this is the image-to-image generation. It's a wide-ranging application such as image restoration, super resolution, medical image synthesis, semantic segmentation, style transfer, virtual try-on system, satellite image enhancement, artistic content creation, etc. Recent advancement in latent diffusion models have significantly improved the generation quality, that computational efficiency, controllability, making image-to-image translation a key technology in modern computer vision and generative artificial intelligence, so that can understand. Right. So we, in our later discussion, we try a few models of image translation, so the generative AI perspective. Next is medical image synthesis. It's a bit application field oriented, but it's very important in the vision application. Medical image synthesis is the process of generating new medical images or converting one type of medical image into another using the artificial intelligence. Now, generative AI models learn patterns from existing medical images and create realistic synthetic images. Just for example, if you are given a CT scan image, can you generate the MRI image? That is the idea. Or a very low resolution X-ray image. Can you generate the high resolution X-ray image? So this is the idea. So this realistic synthetic image that closely resembles the real patient. These generated images help to increase the amount of training data available for the AI models. That improves image quality, support tasks such as disease detection, image reconstruction, image enhancement. Medical image synthesis is widely used in applications such as MRI to CT translation, low-dose CT reconstruction, tumor image generation, medical image segmentation, etc. It also protects the patient privacy, because if you go for a real data, there is a lot of issues of maintaining the privacy of the patient because they are human and there is some copyright thing or some sort of privacy policy out there. So, but synthetically generated image, there is no privacy policy required because it is not belong to any real patient. So it reduces the need of share of real medical images while enabling researchers to develop more accurate and reliable diagnostic systems. Now, generative AI for medical image synthesis leverages advanced deep learning models to generate realistic and anatomically consistent medical images for clinical and research application. Basically, the technique used to GAN, variation autoencoders, diffusion models, which learn the complex distribution of medical imaging data to synthesize high-quality image across modalities like MRI, CT, then PET, and ultrasound research. So this model enables cross-modal image translation, image reconstruction, super resolution, noise reduction, data augmentation by generating synthetic images that preserve essential anatomical and pathological features. So you can understand the generative AI is going to there's a lot of advantage for medical image synthesis. Now, medical image synthesis addresses the challenges of limited unrated data that we have discussed, class imbalance, and patient privacy, while improving the robustness of generalization of different models for disease detection, segmentation, and analysis. Now, what is class imbalance? Now, here there is a few different types of data. let's say there is a grade 1, grade 2, grade 3, grade 4. These are the grades of different uh, say, uh, a particular disease. These are the grade that this patient has a type 1 or grade 1 problem. Grade 2 is more problem, grade 3 and so on. Now, in this kind of thing, for all grade, it is not possible in real situation, the same number of data. So this is called class imbalance. But in the when we generate synthetic data, this class imbalance can easily be mitigated. So that is the class imbalance. As a result, Generative AI has become a key technology for enhancing computer-aided diagnosis, accelerating medical research, and supporting precision healthcare through the creation of the reliable and clinically meaningful synthetic medical evidence. But next is very important, anomaly detection. Now, anomaly detection, what do you mean? It's a bit different kind of vision task. Anomaly detection is a fundamental task in machine learning and data mining, where it aims to identify observation patterns or events that deviate, that is not naturally occur. So deviate significantly from the expected behavior of the system. So that is called anomaly detection. These anomalies, instance often referred as outliers or novelties, may indicate critical events such as equipment failure, fraudulent transactions, cyber attacks, medical abnormalities, etc. Depending on the availability of level data, anomaly detection methods are categorized into supervised, semi-supervised, unsupervised. Now, there is a traditional techniques uh, are there: statistical models, distance-based method, density estimation, clustering algorithms. Where modern approaches employ machine learning algorithms such as isolation forest, one class support vector machine, local outlier factor, deep neural, etc. for this. Now, the primary objective to what is the primary objective of anomaly detection? To accurately model the normal data distribution and detect the deviation while minimizing false positive and false negatives. So despite significant advancement, anomaly detection remains challenging due to the gravity of anomalous events, class imbalance, high dimensional data, evolving data distribution, and absence of leveled anomaly samples at many real-world applications. So you can say that is a very kind of iconic this is anomaly. So how generative AI helps? Genetic models have emerged as a powerful approach for anomaly detection by learning an underlying probability distribution from the data and identifying samples that exhibit low likelihood. That is very important, low likelihood under the learned distribution. So unlike the distributed model or discriminated model that focus on the separating normal anomalous instances, genetic models aim to reconstruct or generate data that closely resembles that training distribution. And during inference, samples typically produce higher reconstruction errors or lower generation probabilities because they are different from the learned representation. So that is the major idea. So deep generative models, including VAE, then GANs, diffusion models, normalizing demonstrated a remarkable performance in detecting anomalies across the image analysis, industrial inspection, cybersecurity, healthcare, and time series monitoring. These models leverage latent responsibility to capture complex nonlinear patterns such as semantic features, enables robust detection in high dimensional dataset. So what are the recent advances? They further improve the anomaly detection by integrating attention mechanism, self-supervised learning, contrastive representation learning, transformer architectures, with genetic frameworks leading to enhanced detection accuracy, robustness, and then across the diverse application problems. Our next task is 3D scene generation. 3D scene generation is the process of automatically creating realistic three-dimensional environments by modeling objects and their spatial relationship. geometry, texture, and light. It actually combines techniques from computer vision, computer graphics, artificial intelligence to generate complete virtual scenes from inputs such as text, images, scene layouts, or partial 3D data. The traditional approaches rely on procedural modeling and handcrafted tools, which often require significant manual effort and lack flexibility. In contrast, modern deep learning methods learn complex spatial and semantic representation from large-scale datasets, enabling the synthesis of diverse, coherent, and high-quality 3D images. So basically, 3D scene generation is basically going to generate 3D modeling or 3D scene from some sort of attributes or some modalities that modeling object, their spatial relationship, geometry, texture, lighting. So you can get an idea from here. These techniques have become increasingly important. Applications such as virtual and augmented reality, robotics, autonomous driving, gaming, digital twin, and architectural visualization. Now here you can see that there is some images. Now from these images, we can find a 3D scene or 3D object description from this. So here also this kind of, and here how they are basically giving. So this is the way that 3D virtualization or 3D scene generation. So there is a different objects, there is geometry and other attributes, okay, and corresponding 3D prepared. Now, what's the generative AI for 3D simulation? The role of or how generative AI improves the 3D. Generative AI transforms the 3D scene generation process by enabling the automatic synthesis of complex and realistic virtual environments from multimodal inputs such as text, image, sketches, or partial 3D data. Now, the state-of-art model like GAN, VAE, diffusion models, transformers models, architectures learn the underlying distribution of 3D data to generate geometrically accurate and semantically coherent. Recent text to 3D, image to 3D framework leverages the large vision language models together with diffusion-based generation to produce high-quality 3D assets with minimal human intervention. So we understand that these generative models improve the 3D generation a lot. These advances improve scene realism, diversity, scalability, and controllability while reducing the manual modeling effort. Despite their success, ongoing research focuses on improving physical realism, object interactions, compute efficiency, and the generation of large-scale interactive 3D environments for next-generation applications like metaverse, immersive digital experience, and intelligent simulation systems. So this is the our future of 3D simulation using generative models. Next topic is face synthesis. Face synthesis is another important research area in computer vision that focuses on generating realistic human facial images while preserving identity, facial attributes, and visual consistency. It involves learning discriminative and semantic facial representation to model features such as facial geometry, texture, expression, pose, illumination. When we discuss some generative model, we understand how this kind of visual attributes are used for this kind of vision. Traditional computer vision approaches employ statistical models, 3D morphable models, and image-based rendering techniques to reconstruct and synthesize vision image. While in recent advances in deep learning enabled the end-to-end face synthesis model that produces high resolution and photorealistic faces with improved identity, preservation, attribute manipulation. So, face synthesis become a key component in the application. Facial recognition, virtual avatars, augmented and virtual reality, digital entertainment, facial enhancement, and image restoration and synthetic recognition for training robust computer vision. These are the examples of this facial parts and corresponding the face synthesis. How generative AI helps is significantly advance the facing by leveraging the underlying distribution of facial data to generate realistic, diverse, and controllable facial. Now, GANs, BA, diffusion, transformers architecture enables high-quality face generation with text prompts, reference images, and rapid responsive representations. These models capture complex facial characteristics such as identity, expression, pose, age, hairstyle, and lighting, while maintaining the visual realism and semantic consistency. So these are the basic attributes that this model capture and produce the realistic face images. Recent multimodal generative framework with large vision language models with diffusion-based generation support text-to-face, image-to-face, and face editing tasks. Such techniques have broad application in digital content creation, virtual humans, biometric research, healthcare, and human communication. The ongoing research emphasizes improving identity consistency, controllable attribute, editing, computational efficiency, and fairness across demographic groups, and the responsible deployment of generative AI to watermarking, governance, tracking, and synthetic video detection. But there is a lot of applications of this. And the styles transfer in computer vision. Style transfer is a computer vision technique that aims to generate a new image by combining a content of one image with the artistic style. It leverages the feature response representation learned by deep neural network to separate high-level semantic content from low-level visual characteristics such as color, texture, brush strokes, and patterns. Some traditional things include CNNs, while approaches employ feed-forward also real-time performance. Style transfer has numerous applications: digital art creation, image editing, photography management, animation, film production, virtual reality, creative content generation. The primary challenge is to preserve the structural integrity of the content image while accurately reproducing the desired artistic style. Now here you can see this is the style, this is the image. You can get the style is called style transfer. Generative AI significantly advances style transfer by enabling the synthesis of high-quality, diverse, and controllable stylized images through deep generative models. At our generative models in GANs, diffusion, vision transformers, multimodal foundation models to learn complex style representation from large-scale images. Unlike conventional methods, generative AI supports text-guided, image-guided, or multimodal style transfer used to generate artistic images from natural language description or reference images while preserving the semantic content. So generative AI for this style transfer is basically like this. This model has its superior visual realism, style consistency, and creative flexibility, making them valuable for application digital art, graphic design, gaming, advertising, virtual environments, and media. So current research focus on improving fine-grained style control, preserving content fidelity, reducing computational complexity, enabling real-time generation, and ensuring the ethical use of AI generated. So these are the basic idea of this is a CNN-based style transfer process. This is the idea. It's a total variation loss used. This is content image, the synthesized image, and style image. Now, the video generation in computer vision, the current task. Video generation is a fundamental task in computer vision. So, on the synthesizing realistic and temporary coherent video sequence from various inputs, including text, image, audio, existing video footage. Unlike image generation, video generation results modeling both spatial appearance for individual frames and temporal dynamics of governed motion and object interaction across consecutive frames. And this traditional approaches on optical flow estimation, frame interpolation, recurrent neural networks, etc. for predict video content. The recent deep learning method have significantly improved the video quality learning, complex spatial representation, and large-scale video dataset. So video generation has a broad application in digital content creation, film production, video editing, animation, virtual reality, autonomous system, robotics, self-care, video simulation, where realistic motion and scene consistent direction. How generative AI helps? Generative AI has revolutionized the video generation by enabling the automatic creation of high quality and temporally consistent video, multimedia inputs such as text prompts, image sketches, and short videos. State-of-art generative models like GAN, variational resolution, transformational Lanza, rich spatial and temporal representation, synthesis realistic motion object interaction. Recent text to video and image to video framework combine large vision language models with diffusion-based generation to produce a photorealistic video with enhanced realism, control with lens. So these are the basic ideas, more or less same for other. So these technologies are widely applied in filmmaking, advertising, gaming, education, virtual assistant, and immersive media. Current focuses on improving long duration video generation, motion consistency, computational efficiency, interactive editing, and responsibility development of AI generated techniques such as watermarking, provenance tracking, and this synthetic media detection. So these are the some applications where generative AI creating big role. So in this lecture, we have discussed different vision tasks using the generative AI models, that image to image translation, medical image synthesis, anomaly detection, 3D scene generation, face synthesis, trial transfer, video generation, etc. These are the vision tasks where generative AI improved this vision task quite a lot. In our next lecture, we start generative modeling. Thank you very much.